Hello again. Time to talk about how we go about making a peptide sequence using individual amino acids. Alright, so one thing to mention is that if you have, let's say, valine, as an amino acid, and you have, an X amount of it present in your solution, technically you'll have a concentration associated with it, but you can basically couple two valines together to make a peptide bond. But the one thing you have to remember is that making an amide out of a carboxylic acid in an amine is not a very efficient reaction. In fact, by all intents and purposes, it's a terrible reaction. So two amino acids like this are not going to form a peptide bond spontaneously. That said, there is a way to activate the carboxylic acid group to turn it into something more reactive. And at least in water, we cannot rely on thionyl chloride because thionyl chloride will literally be destroyed by water. And even if it isn't, the acyl chloride that you will produce will also be destroyed by water. So you have to rely on a different reagent for this to happen. And the reagent happens to be dicyclohexyl carbodiimide, or DCC for short. This reagent activates the carboxylic acid for attack by an amine group, but it is stable under aqueous conditions, so it has that benefit. And I know it looks funky, but the benefit of not having water destroying your reagent is, all the rage these days. So at least that's what I hear on TikTok. So the idea pretty much is that once you introduce DCC into this mixture, you will have this peptide forming. And in the process, the byproduct is dicyclohexylurea, which is a very stable byproduct as well in water. So it is absolutely, the reagent of choice to activate your carboxylic acid and let this reaction happen. Now that said, as far as the mechanism, is concerned, you have the carboxylic acid reacting with the carbon component of this diimide, and one of those pi electron sets will go to one of the nitrogens, creating this intermediate. You will have, probably an amino acid around to protonate that, nitrogen that you've created, that anionic nitrogen. And then that will also free up the protons of that amine. Now, once this happens, the amine goes ahead and attacks the carbonyl carbon of the original amino acid. So you form the tetrahedral intermediate, right? Because that pi bond will move over to the oxygen. So you have this tetrahedral intermediate. And what happens now is that you recreate the double bond. You have that double bond coming back down while kicking away this group. Now this group is having that set of electrons move over to the carbon next door. So this will become a carbon-oxygen double bond. And the pi bond of that carbon-nitrogen bond simply moves out of the way onto the nitrogen. But that creates your unprotonated, or I rather should say, your monodeprotonated dicyclohexylurea derivative. At the same time, you have now created your amide bonds. This thing is protonated at the moment, so that protonation will be taken care of by this deprotonated amide. So we'll simply take that proton away. Those electrons will move over to nitrogen, making the amide bond in between neutral. And now you have formed also your byproduct dicyclohexylurea. All right, now as nice and smooth a reaction as that looks like, the problem will be that if you simply take valine and you add DCC, like if you add, just any amount of DCC, what will happen is that you're just simply going to polymerize this. This is going to continue reacting and reacting, because each time, notice that you are, producing a, a peptide that still has a carboxylate available. So that carboxylate, is going to react, and it will continue doing this thing, forming a polymer. Now, if that's what you're after, well, fantastic. Like, this will do the trick for you. But in most situations, you probably want to have different amino acids in different orders present in your sequence. And so this will automatically be a no-no for that type of approach. So here is where you have to start thinking about how do you go about protecting the amino groups and the carboxylic acid groups so that they're not available for reactivity all the time. And we're going to start with the carboxylic acids. Now, as far as protecting the carboxylic acids, you have a few options. You can um, literally react your amino acids with alcohol in the presence of acids to turn that carboxylic acid or carboxylate ultimately into an ester. And the moment that's an ester, it's no longer available to engage in amide formation, at least not the way that we're doing it right here with DCC. So even if you add DCC here, there'll be no reaction because we have blocked the activity of the carboxylic acid by turning it into an ester. Another way to also go about it would be to react this with an alkyl halide, a good SN2 substrate, to basically take a carboxylate, react it with this, and turn that into an ester as well, which will not react with DCC. So those are two potential reagents you could use to block and protect your carboxylic acid group. Now, as far as removing the carboxylic acid, you have a couple ways you can do this. You can take the ester, react it with acid, or even sodium hydroxide, base aqueous solution, and that will remove the ester group efficiently. And reinstall your carboxylic acid or carboxylate group. All right. Now that's the carboxylic acid. Now for the amine can be protected with also a couple of different groups. One of them is called Boc, which is based on this diterbutyl carbonic anhydride reagent. When you react this with your amino acid, the amine group in particular attacks one of these carbonyls and attaches what at first looks like an acyl group, but this is not an acyl group. This is actually known as a carbamate. Um, All right, so let me show you how this happens first. Then we'll talk about the carbamate. First, you are going to activate one of those oxygens by protonation, and you're going to liberate your amine group for attack. So that amine group will now see the activated carbonyl, so it will attack the carbonyl carbon. The electrons will move over to the oxygen, and you will produce the following tetrahedral intermediate. At this point, you're going to have a proton transfer happening onto the adjacent carbonyl. So those electrons come back to nitrogen. And here you will now generate a molecule that is prime material for expelling out a carboxylic acid on the left side of the molecule. So specifically, we will have the oxygen with lone pairs here, have its lone pairs come back down, generate a double bond. This will happen by breaking the carbon-oxygen single bond shown here over to the adjacent carbon. And what that will also do is move the pi bond onto the oxygen. So the end result will be that we will have a carboxylic acid, or technically carbonic T-butyl carbonate, a byproduct, and we will also generate the following molecule right here, right? So we have the amino acid that was pointing down, now pointing here to the right side, and then what's highlighted in red is what's left over of what we have here in the mechanism. So we have a protonated carbonyl, which can be taken up by the carboxylates to just become a neutral molecule. All right, so as I was saying, this group right here in red is known as the Boc group, and it's a protecting group that can come off very easily from the amine. Also, this group here is called the carbamate functional group. And the reason why we're using a carbamate as opposed to an acyl group is because an acyl group is technically, for all intents and purposes, an amide. And the only way to remove an amide will be to completely hydrolyze the entire oligopeptide, which will obviously defeat the purpose of trying to synthesize a peptide. So instead, we switch over to the carbamate because this group has a higher reactivity and it's a lot easier to remove. And the conditions by which you remove the Boc group do not affect the amide, bonds that you may have in the rest of the molecule. So that's the main reason. Now, as far as removing the Boc group, well, what you do is you simply add trifluoroacetic acid, which will ultimately remove isobutene and CO2 while yielding back your free amino acid. So the way this happens it should protonate the carbonyl of your carbamate. Okay, that's what trifluoroacetic acid is, doing here in essence. Once this is protonated, you'll have pretty much a removal of the T-butyl group. Under these conditions, which are semi-strongly acidic conditions, you can actually generate carbocations, and the T-butyl carbocation is one of the best carbocations to generate. So literally, the electrons of that carbon-oxygen bond will get away from T-butyl. They'll move over to form a new carbon-oxygen double bond, and the pi bond of the protonated, carbamate will simply have its electrons move over, making that oxygen neutral. But now we have also created and formed a T-butyl carbocation as part of the mixture. All right, so now once this is protonated, this um, you know, carbonic component is ready to undergo a deprotonation, basically proton exchange, but also to have its electrons move over to generate CO2 gas. So these electrons will move over back to nitrogen, forming your neutral amine and kicking away CO2 gas. So it's actually a really efficient way of getting rid of this group, which doesn't really affect your amides at all. And then finally, the T-butyl carbocation, that we have generated can simply be um, treated via an elimination reaction, right, where you deprotonate the adjacent CH bond and form your carbon-carbon double bond, also known in this case as isobutene. So that's how the whole thing happens. All right, now one more protecting group that I want to tell you about is the FMOC protecting group, also for the amino component. Now this one, it's a little bit more esoteric in terms of its look. But what you should notice right here is that we do have an acyl chloride, except that this is going to be technically carbamate once more, right? But you have that acyl chloride that is prime material to react with an amine. So you form a carbamate here yet again, including this fluorinyl group. Now, all of this is called fluorinyl methyl oxo carbonyl, which is abbreviated as FMOC. So the mechanism, which I kind of implied already, involves the amino group attacking the carbonyl of that acyl chloride. You have the pi bonds moving towards oxygen. And this tetrahedral intermediate simply reestablishes the double bond. It has the lone pairs coming back down to reform that carbonyl carbon while kicking away the chloro group out of the way. Now you have a protonated carbamate that simply is deprotonated by the chloride or even the carboxylate component of that amino acid. All right, so that gives you that neutral state for your carbamate. And that basically protects the amino group. Now, the deprotection is kind of interesting because for Boc, we're using trifluoroacetic acid, which is an acid. But for FMOC, we use a base, and just a mild base. Piperidine is usually the one of choice, a secondary amine. What this basically does is it removes that entire group by expelling out CO2 gas like we saw with Boc, but it also produces this fluorinyl or this fluorine um, byproduct. And I'll show you in a second how that's formed. But what I want you to notice is that formation of this is highly likely because by forming that double bond, the carbon-carbon double bond that didn't used to be there at the beginning, you complete full conjugation throughout the entire ring structure. And that's the incentive for this reaction to happen. So the idea pretty much is that you use the amine base to remove the proton right at the 5-member ring, and those electrons simply move over to the carbon next door as an elimination reaction to kick away this entire group. Now, this entire group basically has the carbon-oxygen set of electrons move over to the adjacent carbon to produce carbon dioxide. And those electrons from the carbon-nitrogen bond move exclusively to nitrogen. So CO2 is formed in this process. Fluorine is formed in this process. You have your pyridinium cation and your deprotonated, amino acid, which finally gets protonated by attack onto that set of protons, producing pyridine again, as well as your final amino acid. So it's a nice way of kind of getting about it. because this means that you can protect certain amino groups with Boc, and you can protect certain other amino groups with Fmoc, and you can selectively deprotect one type of amine group and not the other, because Fmoc will use basic conditions to get removed, whereas Boc will use acidic conditions to get removed. All right, so this is kind of a prelude to the synthesis of polypeptides, and that's going to be the topic for the next video. But now that we have the building tools to address synthesis and block the corresponding amine groups and carboxylic acid groups, we'll have a good way of approaching the synthesis. So I'll save that for the next video. Sorry for keeping you in suspense, but we're almost at the end, so hang on, hang in there. The good stuff's coming in the next video. Okay, so see you then. Bye bye.